is the notes for 11.6, solving all polynomial equations. If you haven't done so already, make sure you pause the video at this time and read section 11.6 before continuing on. So to begin with, we're going to look at the fundamental theorem of algebra, which states that every polynomial equation, p of x equals 0, of any degree greater than or equal to 1, with complex number coefficients, has complex number solutions. So in other words, if I'm looking at a polynomial, when we say complex number solutions, that means they could be real numbers, they could be imaginary numbers, they could be complex numbers, basically any of the numbers that we've looked at. The fundamental theorem of algebra basically says that every polynomial can be solved with the numbers that we now know. Okay? So from that fundamental theorem of algebra, it's possible to prove that every solution to a polynomial equation has complex coefficients. Okay? And once again, remember the complex numbers include the real numbers. So the fundamental theorem of algebra establishes that every polynomial has solutions. So now we want to get into, well, how many solutions does it have? Okay, well, to do that we have to first define a term, and that term is multiplicity. And it says that the multiplicity of a root r, so any root, in an equation p of x equals 0 is the highest power of the factor x minus r. If the multiplicity of a root is 2, then we refer to it as a double root. And I'm going to take a look at graphically how multiplicity kind of affects what that graph looks like. But basically what we want to do is we want to look at each root to determine its, or excuse me, to each factor to determine a particular root's multiplicity. Alright, example 1 kind of gets at this idea of multiplicity. It says, what is the degree of the polynomial that's given here, and then state the roots and their multiplicity. Well, first of all, let's talk about the degree of that polynomial. I can get the degree without having to put it in standard form, just by looking at each of these factors. If I have an x here and I have a squared, an x here and a fourth, and an x, this is like to the first power, the degree here is going to be x. If you think about it, if I have to multiply each of those together, out of this one I'm going to have 4 x's, out of this one I'm going to have 2, and out of this one I'm going to have 1. Therefore the degree will be 7. Okay, so if I expanded that out, my first term would be x to the 7th power, and actually the leading coefficient on that would be 4. But that's just some things that we know about that if we were to put that in standard form. Now, in terms of stating the roots, well, I can look at the factors to get the roots. This 4, since there's no x there, that's not going to give me any roots, but x minus 3 is going to give me the root of 3. X plus 5 is going to give me the root of negative 5, and x minus 17 is going to give me a root of 17. Now, their multiplicities are dependent upon the powers on each factor. So, since x minus 3 has a power of 2, it's going to have a multiplicity of 2. And at minus 5 has a multiplicity then of 4, and 17 would have just a multiplicity of 1. Okay? So, this one here is called a double root. Okay? This one would be multiplicity of 4, so it's like it counts as 4 roots. Now if you look at those multiplicities, if I add them up, you'll notice that I get 7, which is exactly the same as what I had for degree over here. Alright, I mentioned I wanted to show you how multiplicity affects what the roots look like graphically. So here I have a graph where I have two roots, x equals 1 and x equals 5. And you'll notice that I put the exponents on the on each of the factors as a and b, so they're just going to be something that I can vary a little bit, and then those are going to determine the multiplicity. So right now, if a is 1 and b is 1, they each have a multiplicity of 1. Now as I change any one of these, so if I take this a value and I move it over to 2, you'll notice how that changes my graph. And you'll notice that instead of the graph just going right through 2, it comes down, touches 2, and turns around. Okay. Now if I change it to 3, okay, now it's still going through it, changed again, and it almost looks very similar to the power equation y equals x to the third, but as it's going through that particular value. So the multiplicity kind of makes the actual root where it hits the x-axis, it makes it look like it would if it were a power function. So you'll notice at 5 it looks like that. Okay, go back to 4, just like an x to the 4th power as it hits it. So you can look at the graph of a polynomial, and it will help you kind of determine what the multiplicity of the roots are at any particular place on the graph. Alright, we found from example 1 that when we added the multiplicities together of each of the roots, we had 7, which is exactly equal to the degree of that particular polynomial. Well, it turns out that every polynomial equation with degree n has exactly n roots, as long as we count multiplicities as being that number of roots. So if it has a multiplicity of 3, it's like that root counts for 3 roots, or 3 zeros. Okay, so the multiplicity added together of all of the roots will always be equal to the degree of the polynomial. So example 2 here says how many roots does each equation have? Well, to determine that, all we need to do is look at the degree of that polynomial. So if I look at part A, since the degree of polynomial is 12, we're going to have a total of 12 roots. Once again, that's taking multiplicity into consideration. If I look at part B, I have a degree of 5, therefore there are going to be 5 roots. Now, don't get confused by the fact, I deliberately picked, especially in B, I deliberately picked coefficients that were not real nice. That's okay, as long as there are any numbers that we've worked with, including E. It's alright to have those as coefficients. It's not going to change the number of roots that we're going to have there. Alright, now that we know how many solutions a polynomial has, what we can do is we can apply some of those methods that we previously learned, such as graphing, using the solve function on our CAS, or factoring to solve polynomials. So it says, consider the polynomial p of x equals x to the 5th minus 7x cubed plus 15x squared minus 7. How many real zeros does p have? Well, to do that, I think the easiest method to go about doing that one, so if I look at the graph of that, I've come over to my graphing calculator and I've graphed that function. It asks for how many real zeros. Well, before I even find those, I don't even, it's not even asking me what they are. So before I find them, I know the real zeros are where it intersects the x-axis. So you'll notice that it intersects the axis in exactly 3 places. It's going right through the axis, so we know those are probably of degree 1. So we know that there are 3 places where it intersects, therefore there are 3 real zeros. So over here, the answer to this question is there are 3. Okay. And then part B says how many non-real or complex zeros does P have? Well, if there's 3 real zeros, and I know that the degree of my polynomial is 5, then there must be 2 non-real complex zeros to that polynomial.